Welcome back. In this video, you'll learn about the limit comparison test for series. Let's get to it. Alright, so the limit comparison test is the second of two different comparison tests that we can use to determine the convergence of a series. We looked at the first comparison test in the previous lesson, that was the direct comparison test, where we determined the convergence of a series that was similar to a p-series or geometric series that we did know the convergence of. And we would do that by comparing the series term by term. But sometimes that direct comparison term by term can be difficult depending on the series that we're working with. And so that is where the limit comparison test comes into play. And in my opinion, this is the easier comparison test to use. And so here's what the limit comparison test says. If we have a sequence a sub n greater than 0 and another sequence b sub n greater than 0, meaning that we have two sequences that are positive, and the limit as n approaches infinity of a sub n divided by b sub n is equal to L, where L is a finite and positive value, meaning it's not infinity or negative infinity, but a positive finite value, then we can conclude that the infinite series for both a sub n and b sub n will both converge or both diverge. All right, and so the way the limit comparison test is going to work is we are going to start with one infinite series. So let's say we start with this series right here, a sub n, and we are going to want to find a second series to compare it to, and that will be b sub n. All right, and that series that we are going to compare to the original should be a series that we already know the convergence of, meaning we know whether it converges or diverges. And once we have chosen a series to compare to the original, what we will do is take the limit as n approaches infinity of a sub n divided by b sub n. And if we can show that that limit is equal to a finite value, meaning it's not infinity or not negative infinity, then we will be able to conclude that our original series has the same convergence as the series that we compared it to, right? So if we compare a sub n to b sub n and b sub n converges and the limit is equal to L, then our original series also converges. But if our comparison series diverges and this limit is equal to L, then our original series will also diverge. All right, and so that is the basic idea behind the limit comparison test. And this test is going to be most useful for comparing complicated algebraic series with a much less complicated p-series whose convergence we already know. And so let's take a look at our first example of using the limit comparison test. All right, so here's our first example. For this series, we have the sum from n equals 1 to infinity of n cubed divided by n to the power of 7 plus 9. All right, and so this series right here is not a special type of series that we can immediately determine the convergence of, right? It's not a p-series and it's not a geometric series. And so we're going to need to use a different test to determine the convergence of this series. In this case, we're going to be using the limit comparison test. And before we get started, it is important to note that before you try to use any comparison test, you should always start with the divergence test. See if your series diverges by just taking the limit as n approaches infinity of the expression in your series. All right, so you would take the limit as n approaches infinity of n cubed divided by n to the power of 7 plus 9. And if that limit is equal to a value other than 0, you know that the series diverges. All right, so that should always be your first step for all series when determining if they converge or diverge. But of course, if that limit results in 0, then you can't say anything about your series. You don't know if it diverges or converges. And so that's where you need these other tests, like the limit comparison test. All right, so that's the first step you should always take. But for all the examples we're going to look at in this lesson, these series, if you were to use the divergence test, would all give you a limit of 0, and so you would not be able to conclude anything. You're going to need to use a different test. All right, and so how are we going to use the limit comparison test to determine the convergence of this series? Well, the first thing we need to do is find a series to compare to this series. And so the general strategy that we're going to be using here is for the expression in your series, you're only going to want to pay attention to the highest power of n in the numerator and denominator. And whatever that highest power is, that's what you're going to use for your comparison series. So for example, in our series here, we have n to the third power divided by n to the seventh power plus 9. In the numerator, the highest power of n is 3. And in the denominator, the highest power is 7. And so, the series that we are going to compare this series to will be the sum from n equals 1 to infinity of n cubed divided by n to the power of 7. All right, so we ignore that 9 and just look at the highest powers of n in the numerator and denominator to get our comparison series. Now we can actually simplify this series or reduce it to a nicer form. Note that we have n to the third power divided by n to the seventh power. These would both reduce by a power of 3, right? N to the third power divided by n to the third power is just 1, and n to the seventh power divided by n to the third power will be n to the fourth power. And so this will just be equal to the sum from n equals 1 to infinity of 1 divided by n to the fourth power. And so now you can see that we have a p-series as our comparison series. We have 1 divided by n raised to the power of 4. And so p is equal to 4. That is the value of p for our p-series. And that is greater than 1, which means that this p-series converges. And so now that we have chosen a comparison series and know that it converges, let's use the limit comparison test and take the limit as n approaches infinity of our original series divided by our comparison series, right? We will have n to the third power divided by n to the power of 7 plus 9 divided by 1 divided by n to the power of 4. Okay, and so this is what we do for the limit comparison test. We find our series that we want to compare to our original series and then take the limit as n approaches infinity of the original divided by the comparison. And now all we have to do is evaluate this limit and see if it is equal to a finite value. All right, now we have a rational expression divided by another rational expression or a fraction. And remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so we would say that this is equal to the limit as n approaches infinity of n cubed divided by n to the power of 7 plus 9 times n to the fourth power divided by 1. All right, so instead of dividing by 1 divided by n to the fourth, we are multiplying by the reciprocal, which is n to the fourth divided by 1. And now if we simplify, n to the third power times n to the fourth will be n to the seventh, and so this is equal to the limit as n approaches infinity of n to the power of 7 divided by n to the power of 7 plus 9. All right, and so now we have a limit that you are probably pretty used to evaluating by now. We have a limit as n approaches infinity of a rational function, and so typically what we would do is look at the highest power in the numerator and denominator, and if that highest power was the same in the numerator and denominator like it is here, we have n to the seventh power and n to the seventh power, that limit as n approaches infinity will just be equal to the coefficients of those terms divided by each other, right? So in this case, we would have 1 divided by 1, which is just equal to 1. So you could say that this limit is equal to 1. But if you don't quite remember that rule, you could use the longer method of multiplying by a form of 1 divided by the highest power, right? So in this case, we would have 1 divided by n to the power of 7, since that is the highest power found in the numerator or denominator. And so if you were to simplify, this would be equal to the limit as n approaches infinity of 1 divided by 1 plus 9 divided by n to the power of 7, right? N to the power of 7 divided by itself is 1, and that also occurs down here, but then you have 9 times 1 divided by n to the power of 7, which is right here. Okay, and then the limit as n approaches infinity of 1 is just 1, and the limit as n approaches infinity of 9 divided by n to the power of 7 will be 0, because as this n approaches infinity, this denominator gets larger and larger, and when you have a fixed value such as 9 divided by an infinite value or an increasing value, that whole value is going to approach 0. So this is equal to 1 divided by 1 plus 0, which is just 1 divided by 1, which is equal to 1. All right, so no matter what method you use, you can conclude that this limit is equal to 1. And that value of 1 is a finite value, which means that from the limit comparison test, we can conclude that our original series will converge just like our comparison series. All right, so if I clean up my work here a little bit, we can say that since the comparison series, the sum from n equals 1 to infinity of 1 divided by n to the fourth power converges, then our original series, the sum from n equals 1 to infinity of n cubed divided by n to the power of 7 plus 9 must also converge. And that is going to be our final answer. All right, so because this limit was equal to 1 and our comparison series converged, we were able to conclude that our original series also converges. And so that's the process behind the limit comparison test. You find a series to compare to your original, determine the convergence of that comparison series, and then take the limit of the original divided by the comparison and evaluate to see if that limit is a finite value, and if it is, you can determine that the original series will have the same convergence as the comparison series. All right, let's look at another example. Okay, so next up we have this series, the sum from n equals 1 to infinity of the square root of n divided by n squared plus 3. All right, and so the first thing that we want to do here to use the limit comparison test is to find a series that we can compare to this series. And so once again, the strategy that you want to use is to choose a series that uses the highest power of n found in the numerator and denominator of the series that we're working with. So in this case, our comparison series will look like this. We'll have the sum from n equals 1 to infinity of the square root of n divided by n squared, right? The square root of n, or n to the 1/2 power, that is the highest power in the numerator, and n squared is the highest power in the denominator. So our comparison series will be the square root of n divided by n squared. Okay, now if we simplify this a little bit, we can rewrite the square root of n to be n to the 1/2 power. So let me do that real quick. We'll have n to the 1/2 power. And then to simplify further, we can move n to the 1/2 power to the denominator and make that exponent negative. So this would be equal to the sum from n equals 1 to infinity of 1 divided by n squared times n to the negative 1/2 power. And then n squared times n to the negative 1/2 power can be combined by adding the exponents. And so then this would be equal to the sum from n equals 1 to infinity of 1 divided by n to the power of 2 minus 1/2. And 2 minus 1/2 is 3/2, and so our power is 3/2. All right, and so now we have simplified our comparison series to this series right here, which is a p series. We have 1 divided by n raised to a power of 3 divided by 2. And so p is equal to 3/2, and that is greater than 1, which means that this p series converges. All right, so we have our comparison series for the original series, and we know that it converges, and so now all we have to do is take the limit of the original divided by the comparison. And so we will have the limit as n approaches infinity of the square root of n divided by n squared plus 3 divided by 1 divided by n to the 3/2 power. Okay, but once again, remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so let's just rewrite this limit. We're going to have the original, the square root of n divided by n squared plus 3 times n to the 3/2 power divided by 1. That is the reciprocal of the fraction that we were dividing this expression by. Instead of having 1 divided by n to the 3/2 power, we flip the numerator and denominator to get this expression right here. Okay, and so now if we simplify, remember that the square root of n is n to the 1/2 power. So let me just rewrite that again. We have n to the 1/2 power. And if we multiply n to the 1/2 power by n to the 3/2 power, we will add those exponents. And so 1/2 plus 3/2 is 4/2, and 4/2 is equal to 2. And so this is equal to the limit as n approaches infinity of n squared divided by n squared plus 3. Okay, so n to the 1/2 power times n to the 3/2 power is n squared. And now we have the limit as n approaches infinity of n squared divided by n squared plus 3. And so we have the same highest degree in the numerator and denominator. We have n squared and n squared. And so because those degrees are equal, we can say that this limit will just be equal to the coefficients of those terms divided by each other. And so we have 1 for this n squared divided by 1 for this n squared. So this limit will be equal to 1 divided by 1, which is equal to 1. Okay, and so now we have shown that this limit as n approaches infinity is equal to a finite value. And so we can make the conclusion that our original series will also converge just like our comparison series. All right, so our final answer is that since the comparison series, the sum from n equals 1 to infinity of 1 divided by n to the 3/2 power converges, then the original series, the sum from n equals 1 to infinity of the square root of n divided by n squared plus 3 must also converge. All right, and so that will be our final answer for this example. All right, so here's our next example. We have the sum from n equals 2 to infinity of 1 divided by 4 to the power of n minus 5. All right, so once again, to use the limit comparison test, we first need to find a comparison series that we do know the convergence of. And so far, we have found that comparison series by looking at the highest power of n in the numerator and denominator of our series. Now, in this case, we don't have n raised to a power, but we do have 4 to the power of n in our denominator here. And so this series is very similar to a geometric series, right? We could compare this series to the sum from n equals 2 to infinity of 1 divided by 4 to the power of n. All right, and that is equal to the sum from n equals 2 to infinity of 1/4 to the power of n. And the reason we can say that is because 1 divided by 4 to the power of n would be equal to 1 to the power of n divided by 4 to the power of n, but 1 to the power of n, as long as n is finite, is just equal to 1, and that is divided by 4 to the power of n. And so 1/4 to the power of n is the same as 1 divided by 4 to the power of n, which is what we have right here. Okay, so that's why those are equal. And now you can see that we have a geometric series where we have a value raised to the power of n, and so that value is our common ratio r. We can see that r is equal to 1/4. And when the common ratio is less than 1, like it is here, 1/4 is less than 1, we know that this geometric series converges. All right, so this is our comparison series. We know that it converges, and so now let's take a look at the limit of our original series divided by our comparison series. So we will have the limit as n approaches infinity of 1 divided by 4 to the power of n minus 5 divided by 1 divided by 4 to the power of n. All right, now dividing by this fraction will be the same as multiplying by the reciprocal of that fraction. So if we rewrite this, instead of having that expression, we will have 1 divided by 4 to the power of n minus 5 times 4 to the power of n divided by 1. All right, and so instead of dividing this fraction by 1 divided by 4 to the power of n, we are multiplying by 4 to the power of n divided by 1. And if we simplify, this is equal to the limit as n approaches infinity of 4 to the power of n divided by 4 to the power of n minus 5. All right, now there's a couple different ways that you could go about solving this limit as n approaches infinity. Maybe you'll notice that this is in an indeterminate form, and so you could just take the derivative of the numerator and denominator via L'Hopital's rule, but I'm going to use a different method. What I'm going to do is multiply by a form of 1 divided by 4 to the power of n. Since I see that 4 to the power of n is in the numerator and denominator, multiplying by a form of 1 divided by 4 to the power of n is going to make this limit a whole lot easier to solve, right? If we do that, this is going to be equal to the limit as n approaches infinity of 1 divided by 1 minus 5 divided by 4 to the power of n. Okay, so 4 to the power of n divided by itself is 1. That also occurs right here. And then we have negative 5 times 1 divided by 4 to the power of n, which we have right here. Now, as n approaches infinity, 4 to the power of n is continually increasing. As you raise 4 to a higher and higher power, that value will get larger and larger towards infinity. It is an increasing value, and so we have a fixed value divided by an increasing value, and so that is just going to approach 0. All right, so this is equal to 1 divided by 1 minus 0, which is 1 divided by 1, and that is equal to 1. Okay, and so we have shown that this limit is equal to a finite result, and so we can conclude that our original series will also converge just like our comparison series. And so, if I clean up my work, we can make the conclusion that since the comparison series, the sum from n equals 2 to infinity of 1 divided by 4 to the power of n converges, that our original series, the sum from n equals 2 to infinity of 1 divided by 4 to the power of n minus 5, must also converge. Okay, and so that is the final answer for this example. Let's look at one more example for this video. Okay, so here's our final example. We have the sum from n equals 1 to infinity of tangent of 1 divided by n. All right, so now this is a very different series than what we have looked at so far. All the series that we have looked at up until this point were rational expressions that we could easily see how to compare them to a p-series or a geometric series. And so it's not initially clear what type of series we should compare to this series in order to use the limit comparison test. And so when you're in a situation like this, it's important to remember that there are a ton of different series that you could compare to a series and use the limit comparison test for. There is no one correct series to compare to any particular series. As long as you can show that the limit of your original series divided by the comparison series is a finite value, then you have made a valid comparison for the limit comparison test. And so sometimes your strategy can just be to pick a series that you are familiar with and whose convergence or divergence you know. And then you can test to see if the limit is a finite value or if it's going to be infinity or negative infinity. And if it's infinite, then maybe you want to choose a different series to compare to your series. So sometimes there can be a little bit of guess and check involved with the limit comparison test if you're not 100% sure what you should compare to your series. And so the series that I'm going to pick here, I'm just going to choose the harmonic series, or the p series, where p is equal to 1. So that's just 1 divided by n. And I'm choosing this series not only because I'm familiar with it, but I can also find 1 divided by n within the tangent function, and so I'm thinking there might be some kind of connection there that will lead to a limit that we will be able to solve. And on top of all that, I also know that this series will diverge, right? When p is equal to 1 for a p series, we know that it diverges. And so if I can show that the limit as n approaches infinity of tangent of 1 divided by n divided by 1 divided by n is equal to a finite value, then I can make the conclusion that this series also diverges. And if I can't show that that limit is equal to a finite value, then I will have to choose a different series to compare to this series. But let's try this out. Let's take the limit as n approaches infinity of tangent of 1 divided by n divided by 1 divided by n. Now, if you look at this limit in its current state, what's going to happen to this expression as n approaches infinity? Well, inside the tangent function, we have 1 divided by n, and as n approaches infinity, we have 1 divided by infinity, and we know that a fixed value divided by infinity, or an increasing value, is equal to 0. And so in the numerator, we have tangent of 0 divided by 1 divided by n, which will also approach 0. And so we have tangent 0 divided by 0, and tangent of 0 is equal to 0. So we have 0 divided by 0, which is an indeterminate form for a limit. Specifically, this is an indeterminate form that is compatible with L'Hopital's rule. We can use L'Hopital's rule to evaluate this limit. We can take the derivative of the numerator and denominator separately and then try to evaluate our limit again. And so if we do that, this will be equal to the limit as n approaches infinity of the derivative of tangent of 1 divided by n. That will require the chain rule. So we'll take the derivative of the outside function first and then multiply by the derivative of the inside function. So the derivative of tangent is secant squared. So we have secant squared of 1 divided by n, right? We keep that same inside function, but then we need to multiply by the derivative of that inside function. And remember that 1 divided by n is the same as n to the negative first power. And so if we use the power rule for derivatives on that, we'll multiply the exponent down and then subtract 1 from the exponent, so we'll have negative n to the power of negative 2. And then in a denominator, we will take the derivative of 1 divided by n again, which is still n to the negative first power, so we will have negative n to the negative second power. Now in the numerator and denominator, we have this same expression of negative n to the negative second power, and so those are going to cancel out, and we're just going to be left with the limit as n approaches infinity of secant squared of 1 divided by n. And so as n approaches infinity, 1 divided by n is going to approach 0. And so we have secant squared of 0. In fact, I'll write that out. This is equal to secant squared of 0. And secant of 0 is 1. And so secant squared of 0 will be 1 times 1, which is equal to 1. And so we have found that this limit is equal to a finite value. We can conclude that this series will also diverge just like our comparison series. Okay, so if I clean up my work, we can conclude that since our comparison series, the sum from n equals 1 to infinity of 1 divided by n diverges, then the original series, the sum from n equals 1 to infinity of tangent of 1 divided by n, must also diverge. Okay? And that is true because we found that this limit was equal to a finite value. That is the conclusion that the limit comparison test allows us to make. All right, and so this is the last example for this lesson. And so if you want to see more examples of using the limit comparison test, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.